So I'm really happy to be here to honor my friend Oussama. Oussama, I do remember precisely the first time we met and where we were. It was at École Polytechnique. And I do remember what we were talking about. So I can discuss this now. I did not make any progress on the subject, actually. And I'm happy to see Patrick also. These two people were at École Polytechnique when I was there, and they really influenced my vision of the poor mathematics I'm doing. Okay, so this lecture is not serious at all. It's going to be a series of examples on a subject which I like very much, but I have almost nothing to say. And I hope my student will be able to prove anything in the near future. Yesterday we had a nice conversation for dinner about crocodiles, about sharks, and all these kind of things. So I will start by some zoology of manifolds, which are, for some of them, almost as dangerous as crocodiles or alligators. Start by a picture. So this is a solid torus made out of stone, and I want to carve inside. So I carve in this kind of necklace inside, made out of a solid tori. And I will keep doing this another time. Can you see it? Yeah, okay, I can see it better here. And you understand the process, yeah? You keep doing this, and what you get at the very end is some kind of necklace, which is called Antoine's necklace. It's a very famous object, which turns out to be a counterset. And it has been introduced in the 1920s by Louis Antoine. I say a few words about Louis Antoine. So I'm absolutely not interested in this object at all. But I'm interested in the complement of it in the ambient space. So but for me, by ambient space, I mean S3, not R3. R3 plus a point at infinity. Well, okay, so this was a famous construction. So you get a descending sequence of closed set, and so the intersection is a standard counterset with the standard definition. And so what we can ask about the complement is, for example, what is the topology of it? So there is something which is more or less clear, is that if you take a loop which goes around the torus, I usually point with my laser on this, which is not so if you take a loop which goes out the torus, this loop is not contractible in the complement. It's not a proof, but it's close to be a proof. Now, if you look at this, there is a nice presentation of the fundamental group of the complement, which is called the Wirtinger presentation, that people in knot theory are used to. And there are plenty of generators in the complement of this object here. And you can expect, for example, that any loop which goes inside the torus here will be a generator of the complement. And if you keep doing the construction, then you have a sequence of fundamental group for the complement which forms I never know, projective or injective limit, whatever. Well, this leads to the fact that the complement of this object in the ambient sphere has infinitely generated fundamental group. It's very, very quiet, this room. Now it's not a proof, but you can easily see that if you put a two-sphere in the complement, there is no way that it goes inside the set here. And it shows, at least on the picture, that any two-sphere in the complement will be contractible to a point. So what I'm saying, without any proof, are these two properties of the set I'm interested in. So the A is the necklace, Antoine necklace, and the manifold I'm interested in is S3 minus A. So it's an open subset of S3. So it's a manifold, a 3 manifold, which is open. So what I have not proved, but try to explain in the few words that what I described before, is that X has a fundamental group which is very big, infinitely generated, and all other homotopy groups are trivial. Well, it would need a proof, and I have no time to do it, but it's true. Well, I hope it is true. All right. So this is the first series of examples. So I said series of examples because you can well, I'll explain how you can carve different kind of necklace, but you could, for example, at each step vary the number of solid tori that appear here. So you can construct really a series of 3 manifolds. Oh, here is another series. So, okay, so I have to tell you that all the pictures I stole on the internet, so I have no control on what they are. Yeah. So this is the construction of the standard counter set. The standard counter set is on some interval. And this interval sits in the ambient space, right? Very well straight and so on. Okay, and again, I'm interested in the complement of this set in the ambient space, which is, again, an open manifold, an open submanifold of S3. So here is, so the black intervals represent somehow the counter set, at least at some stage. And here is a circle, which is in complement. It's very clear that this circle you can contract to a point. Just move away from the set. Now, if you take a two-sphere, for example, this one, it's very clear that you can't contract to a point, either inside or outside. So what I'm saying just by looking at the picture is that this counter set gives rise to an open manifold, which is the complement, which is simply connected, but as a second homotopy group, which has infinitely many generators. Of course, again, it's not a proof, but it's quite clear on the picture. And the conclusion of this is that these two counter sets, A, Antoine necklace, and C, the standard one, are not homeomorphic. Well, they are homeomorphic as counter set. Every two counter sets are homeomorphic, but they are not homeomorphic by an ambient homeomorphism. So this is what Louis Antoine did in 1921. So let me tell you a little bit of the story of this guy. So he was a bright mathematician, but he wanted to teach in high school. And World War I started, so he was drafted and went to some place which is, French people know, Chemin des Dames. And he was hit by a piece of metal which crossed his eyes. So he became blind. And he had two friends, Gaston Julia and Henri Lebègue. And they told him, you won't be able to teach in high school because the kids will not accept that as a blind person you teach them mathematics. You should rather teach at university. But you have to write a thesis first. And so that's what he did. Henri Lebègue asked him to prove that any two counter sets in the ambient space in S3 are homeomorphic by an ambient homeomorphism. And it turned out to be wrong, and he exhibited this example. So after that, he stopped. Well, he kept teaching at the university in Rennes, but I didn't find any other work of his. It's very interesting. His good friend was Gaston Julia, who was also drafted same place 3 months earlier. And he didn't lose his eyes, but he lost his nose, actually. And Gaston Julia would wear some kind of mask on his face to protect his face. Okay, this was a tough time. Well, anyway, I don't want to talk about Antoine for a long time. Let me recall the definition of a counter set. So this is a standard definition. I can look here. Yeah. And there is now some kind of classification. The topologists have understood exactly how they behave when you view them in the three-dimensional space or in the ambient space. And there are two types of counter sets. Those who are tame. So by tame, I mean that there is a definition. Tame if there is an ambient homeomorphism which brings it onto a segment or a curve. Well, the standard one that I represented before. And those who are not. So one fact which is not too difficult to prove is that any two tame counter sets are homeomorphic by an ambient homeomorphism. That is, homeomorphism between them extends to the ambient space. And the wild one, which are not tame. And the first one, which I describe, Antoine's necklace, is a wild counter set. Well, here we prove that they were not homeomorphic just by looking at the fundamental group of the complement, but it could be a bit misleading because there are wild counter sets, that is counter sets which cannot be straightened somehow, whose complement is simply connected. So it's really a wild world. Okay, I'm not interested in this set at all, except that I'm interested in their complement as a submanifold, open submanifold of the three-sphere. And I will tell you how little I know on this subject. So Antoine's necklace has been very important in topology. It gave rise to many extensions and a parallel extension like Alexander Horn spheres, and which gave lots of examples of very fancy behavior in topology. Well, anyway, the question I want to address is this one. Take a closed set in the ambient space. What is a good complete metric on the complement? So this was somehow addressed partially by Rodgrover in his lecture, and I come back on this Yamabe problem. Of course, if you ask me what I mean by good, this is part of the question. So this question could be stupid, but I mean, if E is a link, this is the Thurston theory. We know that for most of them, the complement carries an hyperbolic metric. And I'm interested in what would happen if E is a counter set or a fractal set, which I describe in a minute. Okay, so now the question is set. This is a general problem, which I will not solve until my retirement, probably. See, this is not very convenient. By the way, do I look good with this? Or okay, so we have seen two series of examples because we can vary the parameter. I want to introduce a third one, and then try to describe the Riemannian geometry of these open manifolds, and we'll see what is known and not known. Okay. Okay, I want to talk about Whitehead manifolds. Probably most of you know the construction of these very strange objects, but let me recall this. So the story started in 1934 when Whitehead gave a proof of the Poincaré conjecture. And I can describe the proof in 3 points. So the proof starts as, so you remember the Poincaré conjecture, if you take a closed, simply connected three manifold, then it's homeomorphic to a three sphere. So the proof goes as follows. Take such a manifold, X, you pick out a point, what you get is contractible. Well, this is not too difficult, this is just playing with exact sequence and these kind of things. Now the only contractible free manifold is R3, and now if you put back the point, then R3 plus a point is S3. So there is a mistake here, of course. It's not completely wrong, to be honest. It's well, of course, the mistake is on the second point here. But Whitehead was really a smart mathematician, and 1 year later he realized that he made a mistake, and he wrote an erratum, and he gave a construction of the very first example of free manifold, which is contractible and not homeomorphic to R3, and which is called now the Whitehead manifold. So I'll give a quick description of this manifold, and then we'll talk about Riemannian geometry. Okay, so the construction is again using solid tori. So there are at least two different constructions. I used this one, which is somehow simple. You take an infinite number of solid tori, which are included one in the previous one, but the inclusion is not really. The inclusion is not just as a neighborhood of the core of the solid torus. It's just is given by taking in the first solid torus the neighborhood, the tubular neighborhood of some curve which is noted. So again, this picture I didn't draw myself. It would be even worse. But on this picture you can see 4 of them. So let me describe. Okay. So the one which goes around here is the first solid torus, and then there is a second one, which is a tubular neighborhood of some curve with some knot here, which you can see. And you repeat the construction. Then there is a third one, which is a tubular neighborhood of a curve in the second one with the same knot, the same way. So it's recursive. And then there is a fourth one with a knot here. Okay, so the construction is quite clear. You take a curve which goes twice around, and there is a knot somewhere, take a tubular neighborhood, and you repeat the construction. Right? Then on the picture you can see 4 of them. And so then you have a descending sequence of closed set again, and the intersection is some closed subset of S3. I'll show a picture in a minute. And it's called the Whitehead continuum. It's not a counter set, it's some kind of fractal. Or anyway, I don't know what a fractal is, there are no definitions. So. The complement of this closed set is an open subset of the 3 sphere, and the theorem is that this is contractible and not homomorphic to R3. Okay, so here is the Whitehead continuum. Well, at each stage, you see a knot somewhere and the curve going twice around. So first knot, second one, third one, and so on. And they accumulate somewhere here. So you look at this and you think at this fractal set. Well, transversely, it's not difficult to convince oneself that transversely, this is like a standard counter set. So it's, locally, the structure is counter set cross an interval. So look at this and think at this object in the ambient space, and well, the complement is contractible and not homomorphic to R3. Contractible means, for example, simply connected. So you can imagine a curve going around inside here and outside, and the theorem says you can contract this curve to a point. So for Antoine necklace, you were convinced by my argument saying that the curve is not contractible. Now I'm saying it is contractible. And you seem to be convinced too. So I'm really a crook. Well, this is one of the manifolds, not this, but the complement that I would like to understand in the near future. And in particular, what I want to understand is what is the Riemannian geometry of the complement. And this is absolutely not clear at the moment. I'll give a series of results, of known results in a while, which are most of them negative results. So let's go a little bit further. So contractibility is kind of easy. Well, this is cheating again. It's easy if one uses a different construction. To be honest, I describe a descending construction with a sequence of solid tori included in the previous one, and with the intersection and the complement. You could have the same kind of construction with an ascending sequence of solid tori and the same knot. And the union is the same manifold. And if you use this construction, it's much easier to show contractibility. But let me concentrate on non-homomorphic to R3. So one of the property which shows that it's not homomorphic to R3, one possibility is to show that this space, the complement of this fractal set, is not simply connected at infinity, which is a standard notion in topology, but let me recall what it is. So this is a definition, just in case Bourbaki people are in the audience. Let me describe with hand how it works. So simply connected, non-simply connected at infinity means the following. You have a sequence of closed loops going to infinity. So we are in a contractible space, so these loops can be contracted to a point. But any homotopy of this loop to a point has to pass through a fixed compact set. So any homotopy has to have a long diameter. So this is not simply connected at infinity. It means that outside some compact set, the space is not simply connected. And this is a topological property. And a topological property is true for whatever Riemannian metric you can put on this manifold. And one of the questions for which I have at the moment only, well, I have no answer, is what does this property imply for the complete Riemannian matrix? And I must say I don't see. Well, anyway, this is one way to show that you really construct a space, a three-dimensional open manifold, which is not homomorphic to R3, although it is contractible. So let me now briefly recall what is known about these spaces. So I'm talking about Whitehead manifold. So the space is not homomorphic to R3, but if you cross it with R, it's diffeomorphic to R4. There are uncountably many examples. Well, at each stage, you can vary the knot, you can vary the curve, and so on. So you can construct infinitely many examples, and even uncountably many. But it's even worse. If you compare this to the fact that there are only countable closed three manifolds, just by triangulation, it means that there are examples which do not cover a closed manifold. And in fact, it is true that there are examples which cannot cover non-trivially any manifold. That is, what I'm saying is that there are examples, and the one I described is one of the examples on which no group is acting so that the quotient is a manifold. And plenty of them. It's very exciting, I think. I mean, all the techniques that I've been taught when I was a graduate student to work in Riemannian geometry, none of them works here. Group action disappears. Topology does not exist. Well, it exists, but there is no fundamental group. And I find it really exciting. There are also uncountably many examples which do not embed in S3, but this would require a different construction. Yeah. Yeah, I'm sorry. Okay. So this is what is known as far as topology is concerned. So the topologists have worked a lot on these examples and produce lots of property. And now I want to try to understand what we know about the Riemannian geometry of this object. So let me recall that we are working with a space which is contractible, so it could be contracted to a point, not homomorphic to R3, and even a submanifold of S3. And we know the complement. So it should be easy to describe the Riemannian geometry. Well, so there are easy remarks. For example, since it's not homomorphic to R3, it cannot carry a non-positively curved complete metric, just by Adama result. So you could say, well, but what if we take a distance function, which is cat 0, instead of really a smooth metric? Even this is not possible. This is really specific to dimension 3. So there is a result in dimension 3 saying that a cat 0, well, say contractible space is homomorphic to a ball, a standard ball. This is not true in higher dimension, but in dimension 3, it is true. So you cannot think, well, I will do some triangulation and put metrics on the triangle and then arrange the triangulation so that we get the cat 0 stuff, but this is impossible. So I like this result. So I I've cited here Gromov and Lawson papers, one of the papers in IHS, and a more recent one, which I understand less because it relies on K-theory. So this is a nice result. Whitehead manifold cannot carry complete metrics of uniformly positive scalar curvature. So by uniformly positive, I mean with scalar curvature bounded away from 0, greater than 1, for example. So in Gromov and Lawson, they show that if you have a uniformly positive scalar curvature metric, then the manifold cannot be simply connected at is simply connected at infinity. And the proof is really I should not say this because blind is the audience is really very nice. So correct me if I say something stupid, but the idea is you take this sequence of loops and you fill them with minimal surfaces. And these minimal surfaces, which are some homotopy to a point, have to pass to a fixed compact set. And so when you let the loop go to infinity, these minimal surfaces will converge to some complete minimal surface. So this is something that Drickson has developed and used also. But now they show that such a minimal surface, if you are in the ambient space, in a space which has uniformly positive scalar curvature, has to bound in a tubular neighborhood, which is a 2-pi tubular neighborhood, if I remember well. And so this is a contradiction with the fact that it's complete. And well, I mean, it's a big mess now. I mean, with no metric of negative curvature or non-positive, no metric of positive curvature. And even worse, there is a nice recent result which says that Whitehead manifold cannot carry complete metric of non-negative Ricci curvature. And again, it's a study of the minimal surface that float around the manifold. So, yeah, okay, it's a big mess. So there is, however, there is the only positive answer that I know, which brings us back to to Rodgover's lecture yesterday. Since we are in the 3 sphere, so here I put Sn because the question could be asked in any dimension, but you can think to the 3 sphere. You may ask for a constant scalar curvature for the complement of for the Whitehead manifold as a submanifold of the 3 sphere in the conformal class of the standard spherical metric. And the question is, do we have metric of constant scalar curvature which are in the conformal class of the standard metric and which are complete, of course? So this question, as was mentioned yesterday, was addressed first by Loevner and Nierenberg. And they showed something interesting that, ça m'énerve ce truc. Sorry, it's in French, huh? You'd better not listen. And they showed something interesting that if such a metric exists and if the constant is negative, then the set has to be big somehow as far as Hausdorff dimension is concerned. There are also results concerning the non-negative scalar curvature, but in a different spirit. I cited some names here, and the same one that appeared yesterday. But the one result which I'm like to mention a little bit more precisely is quite recent, 2005, by Denis Laboutine, who is in, I think, in Santa Barbara. It's not published. It's preprint circulating, but several people have checked everything. And it says that well, if you're looking at this situation, a closed set in S3 or Sn, and look at the complement and ask yourself, does there exist a constant scalar curvature conformal to the spherical metric and which is complete in this complement? Then there is a criterion, which is, yes, it does, if and only if the set is not thin. Okay, I have to tell you what thin means, of course. So I think it's not published because Denis wanted to get the positive case. So you know, for Yamabe questions, negative case is usually easier. Okay, so let me describe what thinness is. So it's a result in potential theory. So the criterion is very similar to the one that people use to solve the Dirichlet problem on a domain. So if you want to solve Dirichlet problem on a domain, the boundary has to have some property. And I think the criterion for Dirichlet problem is called the Wiener criterion. So this is a nonlinear version of the Wiener criterion. So look at this formula. For any point of the set, you need to have this integral equal to plus infinity. So here we understand everything in the integral. B is a ball, well, infinity is infinity, except this C over there. And this C stands for some kind of capacity. So don't ask me exactly what kind of capacity it is, because it's not the standard electrostatic capacity. It's some capacity related to some other Sobolev space, where the exponents n-2/2 appears. But it really behaves like any kind of capacity. And in particular, well, so let me look a little bit more to this. So you look at the capacity of for any point, the intersection of the ball with the set, and divide by the capacity of the ball. So for example, if the set is, well, if you are at a point P where the set is open, then the ball for small r could be completely included in E. And so what you get here is capacity of B divided by capacity of B, and you get 1. And the r over r is not integrable, so you get plus infinity. So at least it shows you that if you are in a part of the set where it's really big, then this integral satisfies the criterion. It's a bit more subtle. But we can say something for the Whitehead manifold, the one I described here. And more precisely, we have to use this nice property of any kind of capacity, that is, it is monotonic. So if one set is included in the other, then the capacity of the first one, is smaller than the capacity of the other. And we have to use the fact that this criterion has been worked out when the set E is a submanifold. And when the set E is a submanifold, the criterion is very clear. It's related to the dimension of the submanifold. So the criterion is satisfied anytime the dimension of the submanifold is greater than this threshold, which appears everywhere in the story. So now, using these two, we can say that if the set E that we are working with is somehow foliated by manifold of big dimension, bigger than this one, then if locally around any point you have such a manifold, then because of this monotonicity, we can show that the criterion is satisfied. So if you remember the picture of the Whitehead continuum, it was locally standard Cantor cross interval. So there are intervals inside, around every point. And we are in dimension 3, interval is dimension 1, and 1 is greater than 3 minus 2/2. So just by this slight remark, we can show that indeed the criterion is satisfied for a Whitehead continuum, and this is the only positive answer to the question, what is the Riemannian geometry of the Whitehead manifold, that I know. Well, what is a special metric? So the Whitehead manifolds, they carry a metric of constant scalar curvature, which are conformal to the spherical metric, and with a constant which is negative, which is absolutely not surprising. So it's not a big deal, but I wanted to show you how little we know. Sure? I don't know of any, well, it's probably related, but I don't know of any direct relation, actually. And well, it appears also in the, it's clear when you work with submanifold, but it has to be this. Okay, so this criterion is very nice. Well, it's really a potential theory. It's really a nonlinear version, as I said, of the Wiener criterion for domains. All right, so let me switch to another category of manifold for which I can say more interesting results without proof. Well, so one told me that there should be a proof in any lecture, so I had a proof, proof of a Poincaré conjecture. It's wrong, but it's not my fault. So there is a class of open manifold which is very simple. So here I gave a definition, but we don't need to look at precise definition since we are all geometers. It's just infinite connected sum. So how do you do infinite connected sum? You choose a family of closed three manifolds, which I call chi here, will be called F later. And you choose a tree or a graph, infinite graph, and at each vertex you put one member of the class. And then you do connected sum. And you get an open manifold. This is the simplest way to construct open manifolds. Well, open if the graph is infinite. Well, I will talk about trees. It's almost the same. So here are two examples. Graphs, and you glue S3 at every vertex, and you do connected sum along the edges. And what one gets is R3. So R3 is a connected sum of S3s, infinitely many copies of S3. Another example which is clear is S2 cross R. Instead of a half line, you take a line. Okay, so that's a very easy construction. So now is a theorem. So just recall in this definition what is bounded geometry. So I will work with metric of bounded geometry. That makes sense when you are in an open manifold. It means that sectional curvature is bounded on both sides, and injectivity radius is bounded away from zero. And so theorem we proved quite already a few years ago is a complete description of manifold which carry complete metric of bounded geometry and scalar curvature greater or equal to 1, uniformly positive scalar curvature. And the theorem says that such a manifold has to be a connected sum of a finite collection of closed spherical manifolds and possibly some S2 cross S1. So let me explain this a little bit more. So by spherical manifolds, I mean quotient of the three spheres by finite group. So length space, projective space. S2 cross S1 are here just to take care of the sorry, I just probably it's the wine yesterday night. Of the loops, if the graph has some loops, you could replace the loop by S2 cross S1, which is a manifold which replaces a loop. So in other words, I would rather stick to trees for this construction, and you can pass from graph to trees to the price of adding S2 cross S1. So there is a direction which is kind of easy, well known now, which is, I never know what is if and only if, but it's not because of the English, because even in French I never know. But there is a direction which is easy, and it's the following. If you take a bunch of manifold, let's say closed manifold, which have positive scalar curvature, you can glue them together by connected sum, maintaining this property of having positive scalar curvature. So you can refer for this to, again, Gromov and Lawson or Sheleniau. There are two. Excuse me? Yes, yeah. Yes, it's already complicated enough, but you're right. Okay, so there is one direction which is quite clear thanks to these works, and the converse is, well, the converse is Ricci flow. So in the compact case, this is Perelman's proof of the Poincaré conjecture. And so what we had to do to prove the theorem is nothing else than reading Perelman and extend the flow with surgery to non-compact manifold. It's a bit tricky though. It's a bit complicated. We had to change the flow and use an approach which is closer to Richard Hamilton's original approach. But I mean, I don't want to enter this detail. I should tell you it was painful, this stuff, so I don't want to talk about it anymore. Anyway, but the idea is to do exactly what Perelman did, but extending all the stuff to non-compact case. So you have to take care of non-accumulation of surgery in time, but also in space. So there are some extra difficulties. But anyway, it works. I hope. Well, so this is one positive result, but we have this assumption that we should start with a Riemannian metric, which is a bounded geometry. So any open manifold carries a metric of bounded geometry. It's not really a restriction, but still. So we could ask, what if we relax one of these assumptions? For example, let's forget about the injectivity, bound on the injectivity radius. And the answer is we don't know. So far we are stuck with the case where the injectivity radius could go to 0. How did we use the injectivity radius? Well, I can come back on the statement. You see this family here, F is a finite collection. And finiteness comes from the fact that the injectivity radius is bounded below. This is a collection of spherical manifold, length spaces. If you take an infinite collection, then these length spaces will have smaller and smaller injectivity radius. So if one wants to extend this result to the case where the injectivity radius is not bounded below, one should allow infinitely many building blocks and even maybe something else, which I don't know. So this is one of the main difficulties and why we are stuck here. Yeah, okay. So I want to come back to the second example, the second counter set. So here's the construction. So here's well, this is my picture. I'm sorry about that. So here you just lose spheres with cylinders and you go to infinity, and you can see that it's not difficult to see that this manifold that you construct is the complement of a standard counter set in S. And it carries a metric of positive scalar curvature just past construction. Well, we can say a little bit more. In fact, there's a nice result of a Rick chain, which goes back to 1988, which says that if you arrange yourself so that the Hausdorff dimension of the limit is small, then there exists a positive Yamabe metric. Yamabe metric means constant scalar curvature. Positive means that the constant is positive, and as usual in the conformal class of the canonical metric of the three sphere. So how can you arrange the limit set to a small Hausdorff dimension? Well, you can play on the size of these cylinders here. And it's not completely clear to me how you can relate the shape of the counter set at infinity to the size of these cylinders. In fact, it's a nice inverse problem to be studied. I don't understand anything, but I asked the question to one of my students. Maybe you'll find something. Okay, so how much time do I have again? 5? 15? 25 minutes? 15 minutes? It's too much. Okay, thank you very much. You're very generous. Okay, so this is what we call decomposable manifolds are open manifolds which are built using a tree, a finite family of closed manifold, and you do this gluing. Just picking one closed manifold in the family, putting at some vertex, and so on and so forth. Well, one question is, you can build the same manifold with two different trees. Why not? A priori, it's possible. And the question is, can we get a classification of them? Can we say that two such manifolds are homeomorphic or not? Okay, so we got a result which is very similar to the classification of open surfaces. So classification of open surfaces have been looked by only two people in the history of mathematics, maybe more, but at least this Hungarian mathematician Béla Kerékgyártó in 1923. There were some, well, the proof was not complete. And it was fixed in 1963 by Richards. By classification, I mean addressing the same question. You have two open surfaces, infinite topology. When can you say that they are homeomorphic? Well, so this is the question we ask with this decomposable manifold constructed with the help of a tree and a finite family. So, and then if two of them are homeomorphic, we may ask another question: how can we find a canonical presentation? In fact, in this story, there is a very nice interplay between the combinatorics of the graph of the tree and the manifold itself, and it's not completely understood at the moment. But let me state the result about homeomorphy. So we start with a bunch of closed manifolds, x1, xk. Now they are not anymore spherical. There could be any closed three manifold or n manifold also, but let's say three manifold. Well, it's probably better to ask them to be prime. That is, you cannot decompose in connected sum because we are going to make a connected sum. Take a simplicial tree and you construct a manifold M just by putting randomly, as you wish, xi at the vertices. So there are two kinds of situations. When you go at infinity, so you look at some end in the topological sense of the open manifold, you may see some xi which appears infinitely many times. So you collect all these ends, and for xi, you call the collection of these ends bi of m. Well, the space of ends is a counter set again. It's a very famous and old result. So bi of m is a counter set. And now you may have some of the xj which appear only infinitely many times. If this is the case, just count the number of times they appear. And the result is, for a given fixed family F, the collection of these bi of m and edge nj determines the manifold up to homeomorphism. So let me be more precise. Manifold are, so this is, here, this is the set of ends of the manifold M, which is a counter set. This is the set of ends which contains infinitely many xi, which is again a counter set. So if the manifolds are homeomorphic, if well, two manifolds M and M prime are homeomorphic, if there exists an homeomorphism between these two counter sets, well, they are always homeomorphic, but if there exists an homomorphism, we change all bi on one side to the bi on the other side. And if, furthermore, all the numbers, which are finite numbers, are the same, with the same index. Okay, so the characterization is at infinity, except for these, except for these nj here's, which are some kind of local structure. All right, so, well, so this is, so again, I mean, I'm really interested by the interplay between the combinatorics and the structure of the manifold. But again, this is when we talk about a finite family of building blocks. And I have absolutely no idea what happens if you take an infinite family. So this result can be extended in higher dimension, but I don't want to talk about higher dimension anyway. So here are explicit examples. So look at this picture. So I construct three manifolds, taking x1 and x2, two closed prime free manifolds. For example, one is One is a length space, and the other one is a closed hyperbolic manifold. And you do the construction of connected sum like this. So x1, x2, x1, x2, and then x1, x2, x2, x1, x2, x2. And you put all x1s on the one side and all x2 on the other side. And the question, which are homeomorphic here, is not so clear, actually. To show that they are homeomorphic, you have to switch the x1 and the x2s, but you have to do it infinitely many times. So the results, the previous result tells that these two are homeomorphic, and this one is not, just by looking at the space of ends. I'm not sure I understand how you can really construct the homomorphism between the two, but the construction is a bit involved. Okay. Okay, so this is, yeah, okay. This is another question for which we are close to an answer, and it's work in progress as well yesterday. So there is a nice result by Fernando Coda Marquez who proved that on the three sphere, the space of metric of positive scalar curvature is path connected. And so we ask ourselves, is it true again on this open manifold? So path connected up to the action of diffeomorphism. And so with Fernando, I think we have a proof, but it's a bit early to state a theorem. It's more tricky when you work with an open manifold because you have to control what happens at infinity as usual. Okay, so let me finish. So I've been talking about Whitehead manifold, about this complement of standard counter set. I've said nothing about the complement of Antoine next legs. It's just because I have nothing to say, except maybe something that I skipped. I'm sorry, let me come back to, I can do it this way. Oh, okay. So you remember the construction of this necklace. I mean, you take a solid torus, inside you carve a necklace of solid tori, and you keep doing this. You could do this with higher genus construction, right? Genus 2 or genus 3, and genus 3 inside. And you get also a set whose complement is an open manifold. I mean, the possibility of construction manifold is endless. And you can ask yourself, what is the metric on the complement? So the only answer that I know, which is completely indirect, is this one. So a very nice result, which is due by Juan Soto and Stover, which says that there exists a counter set in the three sphere so that the complement admits a complete hyperbolic metric. It's quite unbelievable for me because all the examples that I've looked at do not show any possibility for having a hyperbolic metric on the complement, but it's true. It's not constructive. The theorem says there exists, and in fact, it's a work on representation. It follows very closely the work of Thurston on representation into PSL2 of C. But what does E look like? This is not clear. But after discussing with Juan Soto, I mean, we arrive at the conclusion that the counter set is certainly not explicit, but it's probably some kind of Antoine's necklace, but with higher genus. Antoine's necklace cannot be such a counter set because there are too many toris, and toris do not go along well with the hyperbolic geometry. But it's probably some kind of higher genus stuff, and it's not so easy to check that. Well, anyway, this complete hyperbolic metric, of course, is not, well, it's not closed, it's open, but it has infinite fundamental groups, so it's kind of a wild example of complete hyperbolic metric. Well, and then I finished by the motivation. It's very strange to finish a lecture by the motivation, but why not? I mean, the question we started with is, well, after Perelman's work on the geometrization of closed manifold, what could be a good statement for the geometrization of open manifold? And to be honest, at the moment, we don't even know how to state a good question. And the reason is that, so let me recall the closed manifold construction is start by two decomposition, one which is due to Kneser and uniqueness by Milnor, where you decompose a closed three manifold into connected sum, a finite connected sum, and it's kind of unique. And one which is due to Jacques-Schelen and Johansen, where you decompose a three manifold into a bunch of along a bunch of tori into pieces which are geometric. This is a geometrization, I mean, in short. And the T2 here are incompossible tori. While in dimension 3, and Perelman proved that the pieces are geometric. In dimension 3 and for open manifold, none of the two first steps is true. For example, you can have open three manifold. It's easy to imagine where the essential spheres accumulate, so that you cannot just cut a long essential sphere into pieces. And needless to talk about the second decomposition. So there is not even a way to start to look at this question. So the only thing that we were able to do is to look at examples. And that's what I tried to present today. Some example of open free manifold, which I think are worthwhile studying, and well, for young people, for graduate students. And I finished. And so thank you, Usama. And there is no mistake here. I mean, the S makes sense here. You should ask to Usama what it means. Thank you very much.